Welcome to the course module of Communication Engineering. And in this lecture today, we are going to learn about the joint distribution and conditional probability of two continuous random variables. So in my previous lectures, I have already explained about the joint distribution in the case of discrete random variables. So now in this lecture, we have to see how to define the joint distribution for continuous random variables. So let's see the mathematical expression, the mathematical definition for joint cumulative distribution function for two random variables x and y is mathematically defined by this particular expression. So this joint CDF will be f x y, x comma y will be equals to this particular probability. So this represents you that what is the probability that the random variable x will be less than equals to x and random variable y will be less than equals to y. So this is the meaning of your joint cumulative distribution function. So here, these two random variables x and y should have this particular probability. This is the meaning of your CDF, right? Joint CDF. Similarly, as we have already defined, if we want to define the joint probability density function, then normally we know that in my previous lectures, I have already explained that this joint probability density function is actually defined. It is defined as the derivative of your cumulative distribution function. So here, as we know that we are having two random variables, and therefore while defining the joint PDF, this joint CDF should be we have to take the derivative with respect to the both random variables x and y. So what does it mean by having this particular probability? That we can understand by seeing certain examples. So for example, let us say that this is one of the data, okay, in which we are actually showing that there is a maximum temperature and minimum temperature over the year, okay, in a particular place. And here we also have the data corresponding to rainfall. So this particular blue line actually representing the rainfall over the years, and here the two lines here, red one is showing you the maximum temperature over the years, and the green line showing you the minimum temperature over the years. So suppose if this particular maximum temperature is being represented by a random variable capital X, and this blue line, which is representing the rainfall, is represented by the random variable capital Y. So if we want to know this particular probability, we may ask that what is the probability that the maximum temperature in a certain month will be less than 35 degree, and the rainfall, the corresponding rainfall will be certain 5 centimeters, okay? So that way we can ask in a certain month. So this may be the conditional or this may be the joint cumulative distribution function. We can ask this particular probability, right? So this is one of the example. You can also take some other examples to define the joint distribution. For example, as we know that when we move in the upward direction from the Earth's surface, the temperature and the pressure is actually having certain variations with respect to the height of your with respect to the height, okay, from the Earth surface. So when these things will change with respect to height, okay, we can ask that what is the uh, pressure and temperature, okay, at a certain height, okay, at a certain height. So that probabilities we can actually define. So this way we can understand that we are having two random variables, and mostly these two random variables should be have a certain dependence, right? So that time we have to define that what is the joint probabilities, what is the joint probability. So this way we can have the joint CDF. This is the mathematical definition, and this way we can define the joint probability density function. So now here we can see that because it is a joint PDF, after all, it is a probability density function. So what we can have, we already know that the area under the PDF curve is always equals to 1. So because it is having joint PDF, then this integration we have to do with respect to both the random variables x and y. So normally we have to integrate this from minus infinity to infinity for both the random variables x and y, and this value should be equals to 1, right? So in the case of single random variable, normally what we say that the area under the curve should be equals to 1. But when we have two random variables, we normally call it as it is the volume carved by that particular surfaces will be equals to 1. Okay, so it is representing the volume, right? So this volume should be equals to 1. So in general, if we wish to get the joint probability, okay, so in general, we can calculate any probability. So let us suppose that if we want to get this particular probability. So if we want to calculate the what is the probability that this random variable capital X. So please make this correction. Okay, here I have written a small x, but it should be a capital X, right? So we can get this joint probability that what is the probability that this particular random variable capital X will be in between x1 to x2, and what is the probability that the random variable capital Y will be in between y1 to y2. Okay, so if we want to get this particular probability, then this probability can be calculated by using the joint probability. Okay, so we should have the joint probability density function. So let us say if we have this joint probability density function, then this must be integrated from this limit, okay, x1 to x2 and y1 to y2. So this particular integration will give us this particular probability. So this way we can calculate any probability. So now here we can also define the way I have defined in the case of discrete random variable. I defined the marginal probabilities, right? So similarly here I can also define the marginal density, okay, because it is a continuous random variable. We can also define the marginal density. So normally these marginal densities are called as the individual probability density, right? So this can be calculated from the given joint probability. So if we have any joint probability, then from the joint probability we can calculate the individual probabilities, right? Individual probability density function. So those probability density function is called as the marginal density function. So how to calculate that? So that to calculate, we have to use this particular formula. So what is this formula? So suppose that if we want to calculate the marginal density function corresponding to our random variable capital X, then it can be calculated if we take this joint probability density function, and if we integrate it with respect to y. Okay, so here you can see that because this joint PDF is the function of both x and y, and because we are just integrating this function with respect to y, and we are putting this limit from minus infinity to infinity, then we are going to get with respect to y, the probability is going to be equals to 1. Okay, so here the function that we are going to left after doing this integration is the function of x only, and that will give you the probability density function corresponding to your individual probability density function corresponding to your random variable x. Similarly, if you want to get the marginal density function corresponding to your random variable y, then you have to do this integration with respect to variable x. So this way we will be able to calculate this probability density, individual probability density functions. Now, similarly, this individual CDF can also be calculated. So how to calculate this individual CDF? So suppose if we have any CDF, right? We have the CDF expression. Normally, if we put this particular limit, this particular probability. So suppose if we want to calculate what is the fxx, okay? So this can be calculated if we have this expression for fx, xy. So if we calculate this particular probability, fxy, x comma infinity. So what does it mean by x comma infinity? It is the probability that this random variable capital X will be less than equals to X, and what is the probability that the capital random variable Y will be less than equals to infinity. So as it is a random variable Y is less than equals to infinity, we know that that probability will become 1. Okay. So similarly here, if you want to calculate F Y Y, then this will be giving you this can be obtained if you substitute this as infinity, right? So this x will be equals to infinity. So this way we can calculate the individual cumulative distribution function, or we can calculate the individual probability density function from the given joint CDF or joint PDF. So this way we can do this. We can calculate these functions, right? So now we can also see what is conditional probability in the case of continuous random variable. So as in the case I defined in the discrete random variable case, a similar case we can also analyze for your continuous random variable. So normally this definition, if you see its mathematical definition, so there when we discussed about the discrete random variable, if you remember, we talk about the probability, okay? But when we have the random variable to be a continuous random variable, that time we have to define the probability density function. It is not probability, but it is a probability density function. So here we can see that this probability density function will be defined by this particular conditional probability density function will be defined by this particular expression. Here is we have denoted it by small p. Okay, remember in the case of discrete random variable, I represented it by capital P. That was representing the probability, right? So here this represents you the conditional probability density function. What is the probability of having x for a given y? Okay, so here this yj is already occurred, and then we have to find out what is the probability of x. So normally it can be written in this way, or this can also be written in this way. Okay, probability x given y, so it can be x oblique yj multiplied with delta x. Okay, so what does it mean? So the meaning is that what is the probability that this continuous random variable x will lies in between x to x plus delta x when y is equals to yj. So this is the probability. Okay, this is the conditional probability. So what it denotes? It denotes the probability of observing this random variable x in the range of x to x plus delta x. So in between this particular range, there will be a certain probability density, okay, that we have to calculate for the given this condition y equals to yj, right? So now we can also calculate the your joint PDF in terms of your conditional probability density function. So again, I will use the same equations that I have used for the discrete random variable. So those who are watching this video first, please do watch that particular video. Okay, that I have discussed about the discrete random variable. Then you will be able to follow this video easily, right? So we can write this joint PDF in terms of conditional probability by writing this expression. Okay, so if we want to get this joint PDF, okay, joint PDF x y x comma y, then this can be written as p y y p uh, x given y. Okay, so this will be our joint PDF, and this can also be written in other way around, that we can write this expression pxx py given x. Okay, so you remember here we are writing this probability pyy first, and then we are writing a conditional probability that for a given value of y, what is the probability of getting this particular x. Okay, so x should be in the range of this particular range. Okay, so x to x plus delta x. Similarly, this joint PDF can also be written uh, for a given x, right? So if there is a given x, then we have to calculate this conditional probability for the given x. What is the probability of observing this y? Okay, so here we have to write that probability of the given x pxx, and then it should be multiplied with this conditional probability. So again, we can use the base rule that I have defined. So I explained you about the base rule, that the one conditional probability can be defined in terms of the its reverse conditional probability, right? So again, we can write this for the continuous random variable. So if we wish to write this particular conditional probability, what is the conditional probability density x given y, then this can be written as, so you remember these are all the probability density function. Okay, it is not probabilities, but it is the probability density function in the case of continuous random variable. So here we can write this p probability density function x given y will be equals to probability density x multiplied with probability density y given x divided by probability density y. Okay, so this is the conditions, right? This is the base equation, base rule, right? Based on the base rule, we can write this particular expression. So here, one thing that we have to note down is here I have taken both the variables, both this random variables are continuous random variable. But this can also be written for the mixed random variables. We can have certain conditions in which the one random variable will be a continuous random variable and the other random variable will be a discrete random variable. In that case, we can have the mixed random variable. Okay. So again, we can write the same expressions. Okay, we can write the same expressions, okay, by following the base rule. So here you can see that suppose that we are having x as a discrete random variable and y is the continuous random variable. So in that case, if we want to write the base rule, then if you write this particular expression, okay, so here we are calculating we are calculating the probability density of getting the x for a given y. Okay, so when this x is a discrete random variable, in that case, this probability density function will be converted into the probability. Okay, so therefore what I have written here is because x is your discrete random variable. Fine. So when we are defining, so this probability density function will be converted into the probability. Okay, so it is the probability that, what is the probability that this random variable x for a given y. Okay, so this is now probability instead of probability density function, right? So here it is the probability density function for your continuous random variable y. So that I have multiplied over here. So this will be your probability density function. Why it is probability density function? Because it is a continuous random variable. Fine. So similarly, this expression here, it is a continuous random variable x. But here, if you take this to be a discrete random variable, then this probability density function will be converted to your probability. Okay, so this will be converted into probability. And here we have to write the conditional probability for y given x. So that will be written as in the probability density function, right? So because we are calculating the probability density function for a given x, right? So because y is a continuous random variable, it should be a PDF, right? So this way, we can also follow for any mixed random variable cases, right? So as I explained you about the discrete random variable, that if we have any conditional probability, okay, then we could do the summation over all the provisional means conditional probability, and that summation was equals to 1, right? So similar expression we can also get in the case of continuous random variable. So if we have any continuous random variables, then in that case, we can have this particular expression. So if we do this integration from minus infinity to infinity with respect to this variable x, then this lead to equals to 1. So how it is 1? So as we have already seen in the discrete case that summation is equals to 1. So this can easily seen here, this proof we can easily see that. So this particular conditional probability p x given y can be written by using this base rule. Okay, so here we have already defined this conditional probability, right? P x given y, so that can be equals to this joint probability p xy divided by pyy. Okay, so that you can write here, and then because pyy we don't have, actually it will be treated as a constant, okay, and it cannot be integrated. Fine, so it will be outside the integration. Okay, and here this integration will go from minus infinity to infinity, right? So once we'll perform this integration of joint PDF. Okay, so I explained in the previous slide that because it is a probability and density function, right? So when we do this integration, okay, if we do this integration, then we are going to get the marginal density function. Okay, because it is we are doing this integration with respect to the variable x. The marginal density function that we are going to get is individual probability density for random variable y. Okay, so this particular expression will lead to your random variable, this your individual probability density function corresponds to your random variable y. So this denominator and numerator will cancel out, and this will be giving you equals to 1. So this is corresponds to a similar expression we also got in the case of discrete random variable, but instead of this integration, we had the summation, right? So now we have to see one more thing about what is the independent random variable. Okay, so let's suppose that if we have the two continuous random variables, and those random variables are independent. So here we have to first understand what is the independence means. So basically we can have the two random variables which don't have any interdependence, right? So we can have certain such kind of means variables, right? We can have such random two different random events, and that events may or may not means will not be depending to each other. So if it is not depending on each other, then obviously what will happen that if you want to calculate this conditional probability, suppose if you want to calculate the conditional probability, that what is the probability that this x will occur for a given y, then because this x and y's are independent, therefore this will be same as the probability density of x itself, right? Similarly, if you want to calculate what is the probability density of y given x, then again it is going to be the independent probability density function corresponds to y, because it is not depending on x. Okay. Similarly, if it is not depending on y, it will be a individual probability density function, right? So this way, we can have this probability density function. So for all the independent continuous random variables, okay, normally if you calculate the joint probability density function, then this joint probability density function, because here we have defined as a conditional probability, okay, in the terms of conditional probability. So this conditional probability will be going to give you p x x, right? And therefore it will be the multiplication of the individual probabilities, right? Individual probability density functions, right? So this way we can have the joint probability density function for your independent random variables, right? So here you can see that a similar way we can also write the CDF, okay, your cumulative distribution function for independent random variables. So how to get this CDF for independent random variables? So let us say this is our fx x comma y. So if we want to calculate this particular probabilities, right? So this is the probabilities denoting you what is the probability that x will be less than equals to x. Okay, so that can be calculated by writing the this integration. Okay, if we have this joint probability. So because we have this joint probability, I have just changed this dummy variable for integration purpose. So it will be v, and this is w, and we have to do this integration with respect to v and w. Okay, so this limit will be going from minus infinity to x, right? And this will be minus infinity to x, right? So because we have already seen, because of the independent random variable, the joint probability density function can be written into this product of these two independent probability density functions. So that we can write here, okay? And then we can separate out these two integrations, right? So if we separate out this two integration, this is corresponds to fxx multiplied with the fyy. So here we can easily see that this is our the cumulative distribution function for independent random variable will be equals to the multiplication of the individual CDFs corresponds to your random variable x and y. So you remember there are certain examples in which you can show that the variables are independent. Okay, there could be certain variables that can be independent. The dependent variables, I have explained you in the previous slide that we can have like what is the temperature and what is the humidity, because temperature and humidity of atmosphere is depending on each other, right? But there could be a certain variables in which there is no dependence, right? We can have such variables, there will be no dependence on each other. Okay, so if one variable is changing, right, there will be no impact onto the other variable. So there will be no such correlation between the two, and such random variables could be regarded as the independent random variable. So I will stop here. Okay, so in the next lecture, I will discuss a few more important topics. So if you have any query, if you have any doubt, you let me know with your comments. So thank you for watching this video.